0. That's how many of the answers inside a neural network were ever written by a human being. Nobody typed them in, nobody coded them one by one. And somehow, the thing learned them anyway. There's one number buried inside every one of these systems that explains how it learns at all. Almost no one can name it. Keep it in mind.
The premise is wrong, right up front. Fenrir here. People imagine a giant rulebook sitting inside the machine, some engineer typing in every fact. There isn't one. There was never a rulebook.
Yeah, last time we followed one question from your keyboard to the answer. Today we go underneath it, to the part nobody shows you. How the thing learned to answer at all.
This is Erica, and the honest starting point is a wall of dials. Picture millions of tiny knobs, each one just a number. At the very start, before any training, every single knob is set completely at random. That is the whole machine on day one. Pure noise, wired up and switched on.
Take that seriously for a second. I'm Tiffany, and the version going around online is that engineers handwrite the smarts line by line. They don't. Verdict. Busted. What they actually build is that wall of knobs and a way to tune it.
Careful. The word tune is doing an enormous amount of work in that sentence.
It is, and that's the whole video. You take those random knobs and nudge them over and over millions of times, and behavior that looks like intelligence slowly falls out of the noise. No human wrote the behavior. They wrote the tuning, and the tuning wrote the rest, the way a kid learns to read by practicing, not by being handed the rules.
None of this is even science fiction, by the way. The very first machine that learned exactly this way was built in 1958. It filled an entire room. Before we open the machine up, Tiffany, you pulled the question people keep leaving on this exact topic, almost word for word.
I did, and honestly, it's the heart of the matter. People keep asking this. If nobody programs the answers, how does a neural network actually learn anything? The honest answer is one word: practice. Millions of rounds of it, exactly like a kid learning to read.
Practice. That's the honest one-word answer. And the rest of this video is just the how. So let's open the machine up and build one of these voters from scratch.
We build one voter first, then a whole crowd of them. This is layer 2 of the AI stack, the layer everything today runs on. The weights. The billions of learned dials that quietly hold everything a model knows, and it starts with a real thing in your head, a neuron. A brain cell takes in signals on one end, and if they add up past a point, it fires a signal out the other end. That's it. That's the part the whole field borrowed.
Watch the artificial version, and it's almost insultingly simple. An artificial neuron is a weighted vote. Each input comes in, gets multiplied by a weight, a number saying how much that input matters, and they all get added.
Give me the everyday version. Weighted vote means nothing yet. So here, car insurance. Think about how they price you. Your age is one input. Your accident history is another. Your zip code, another. Each one carries a weight. Accidents count heavily. Your zip code counts a little, and they add every weighted piece into one number.
The premium. Right, I see exactly where this goes. Same shape a second time because seeing it twice makes it stick. A credit score. Missed payments weigh heavy. One late library fine weighs almost nothing, and it all adds up to a single number that decides something real about you.
So what's the same in both, in one sentence? You take a pile of inputs, weight each one by how much it matters, and add them into a single verdict. That is a neuron. That is the whole cell.
There's a catch a cover charge doesn't have. In a fresh network, no one sets those weights. The way the insurance company learned its back up. This is the kind of thing I chew on walking without a destination. The insurance company had decades of real claims behind its numbers. A newborn network has nothing. Every weight is random.
Right, and this is where it turns from a cell into a brain. One neuron is a single weighted vote, useless alone. But you wire millions of them in layers, each layer feeding the next, the first layer's votes becoming the second layer's inputs. And that stack is the network.
This exact idea is old too. That's the whole answer to whether any of this is new. It isn't.
Remember that room-sized machine from the top? A researcher named Frank Rosenblatt built it back in 1958. A layer of exactly these voters taught to tell shapes apart by tuning its weights. It's in the Smithsonian now. The idea is almost 70 years old. What changed is scale.
How much scale, though? Take a guess before I say it. In one round of training, how many of these dials does the machine tune at once? 1,000? 1,000,000?
A few 100,000 maybe? I mean, a big model, so a couple million tops.
Not close. One well-known model, GPT-3, has 175 billion of them. Billion with a B.
175 billion dials, all nudged together every single round. Hold that number, because there's a step coming that has to tell every one of those billions of dials which way to move at once. It sounds impossible. It has a name almost no one has heard, and we'll get to it.
One thing before the next part, and then we move right on. If any of this is clicking, tap that like, hit subscribe, and ring the bell for the next one. It takes a second, it costs nothing, and it helps more than you would think. Everything so far keeps the network clueless. Random dials, random guesses. The next 10 minutes is really about one thing, and wait until you see what a single number can do. Before a machine can get better, it has to notice it's wrong. Tiffany says that part's simpler than people think. Finmer says that's exactly where the whole miracle hides.
It is simpler than people think. Look at what actually happens. You show the network a handwritten 3. Right now, with random weights, it shrugs and guesses. I don't know, maybe an 8. So you compare its guess to the real answer, and you score how far off it was. That score has a name. The loss.
Hold on, source that for me. Where does that score actually come from, and who says it's the whole game?
The math itself, straight out of how these things are trained. And here's the honest limit, so nobody oversells it. The machine doesn't understand it was wrong. It just measures how
many it got wrong. A tally.
Not how many, how far. And that's the piece everyone gets backwards. The loss is a distance, not a count. Nearly right scores low. Wildly wrong scores high. It's measuring the size of the miss, not tallying misses.
Fine, I'll take the correction. But measuring the miss is the trivial half. The miracle, the actual miracle, is what you do with that one number next. To improve, you have to reach back into 175 billion dials and tell each one individually nudge up or nudge down from a single score. That's the impossible part.
So attack that head on, Tiffany. Finmer's strongest claim is that one number can't possibly steer a billion dials. Answer that.
I'll grant him the setup. Verdict, half true. One number can't do it alone. You need a second trick to spread the blame backward through the layers. And honestly, that trick is the next chapter. But the loss is the starting gun. Without a number that says how wrong, there is nothing to shrink and nothing to learn.
And if it misses by a hair instead of a mile? Same machinery, or does a tiny error break it?
Same machinery, and the elegant part is this. A tiny loss makes a tiny nudge. A huge loss makes a big one. The size of the mistake sets the size of the correction, automatically. It self-scales.
Let me land that for everyone watching. The loss is one honest number for how wrong the guess was, and the entire goal of training is to shrink that one number over and over. That's the number I promised you at the very top. That's it. That's the whole secret almost nobody names.
There's a cost hiding inside it too. Shrink the loss the wrong way, and the same rule runs in reverse. The network gets confidently, beautifully worse. That number cuts both directions. And next we show you how it goes right.
The point stands either way. One number in, a billion corrections out.
One tool measures the miss. The next one aims the fix.
Right tool, right job.
The number's the easy part now. Actually shrinking it, that's where a single picture does all the work. Picture a ball on a hillside in thick fog at night. You can't see the valley floor. All you can feel is the tilt of the ground right under your feet. So what do? You take one small step in the steepest downhill direction. Then you feel again. Then you step again. Do that enough times, and you reach the bottom without ever once seeing where you were going.
And that's training. Almost exactly. The valley floor is low error. Every step is one tiny nudge to the weights.
The trick's almost that simple. I mean, most of it, the rest is just scale. It even has a plain name that sounds fancier than it is. Gradient descent. Gradient is a math word for steepness. Descent means going down. Feel the tilt, step downhill, repeat. That is the entire engine under every AI you have ever used, and you can watch it happen. This is the error over a typical training run, falling step by step as the ball rolls down. It starts up above 90% wrong, and it drops, fast at first, then slower, closing in on.
Skip ahead. How does one number steer a billion dials downhill?
That's exactly the step I promised you 2 chapters back. And it finally gets its name, backpropagation. And honestly, the scary word hides a boring, beautiful idea. Bookkeeping. When the final answer is wrong, you walk backward through the layers and you do accounting. This last dial pushed the wrong way, so it takes most of the blame. This one barely mattered, so it takes almost none. You assign every dial its exact share of the error, layer by layer, all the way back.
And remember, this blame assignment happens to all 175 billion dials at once, every round.
And it's not new, which people always find wild. The version going around is that this is some 2020 breakthrough. Busted. In 1986, 3 researchers, Rumelhart, Hinton, and Williams, wrote it up in Nature, and it barely made a splash for years.
It's like my big rescue dog Loki, because of course, nobody explains the rule to him. You just reward the right move 100 times until it sticks. One question first though, which is doing the learning, the downhill part, or the bookkeeping? People say gradient descent and backpropagation like they're the same thing.
Fair question, and the distinction actually matters. Backpropagation is the accountant. It figures out the blame, which direction each dial should move. Gradient descent is the hand on the dial. It actually turns each one a hair in that direction. One works out the steepness. The other takes the step. 2 different jobs, and you need both.
And people ask this constantly, so let me just answer it head on. Someone always writes in, why does training take months and a warehouse of computers? Because you run that entire loop, guess, score, blame, nudge, not once, but billions of times over a mountain of examples. One pass barely moves the needle. It's the sheer number of repetitions that turns noise into skill. Miss that, and none of it makes sense.
Fine, that all works, but none of it explains why you need so many layers stacked up. A big pile of votes is still just votes, unless...
Unless the depth is doing something the width never could. It is. And this is the part people rewind, so take it slow.
The reveal is this. When you stack the layers deep, each layer learns to see something the layer below it couldn't. And nobody tells it what to look for. It invents the categories on its own.
Look at a network learning to recognize faces. Peek inside it, layer by layer, and you find a ladder. The bottom rung sees raw pixels, just dots of brightness. The next rung up learns edges, little lines. Above that, corners and textures. Higher still, actual parts, an eye, the corner of a mouth. And at the very top, whole faces. Each layer builds on the one below, from raw static at the bottom to something that reads a face at the top.
And nobody wrote edge detector on layer 1 or face on layer 5. That's the part I can't get over. So let's bring in someone who's stared into these things for real. Marisol Vance knows how these networks learn, from the weights up. Marisol, are you there?
I'm here, and I'd reframe one thing right away. The question isn't how did we teach it edges and faces? We didn't. The right question is why those features appear at all unasked. That's the strange true part.
So why do they?
Because edges are simply the most useful thing a bottom layer can build to help the layer above it lower the error. 9 times out of 10, if a feature helps shrink the loss, training keeps it and sharpens it. Edges help read shapes, shapes help read parts, parts help read faces. The hierarchy isn't designed, it's discovered because it works.
One question first, honestly. You can't actually see all of it in there, can you?
Honestly, no. The clean feature layers I know cold, the edges and the parts, that's well mapped. But the deepest layers of the biggest models are a different animal, and anyone who claims they read those fully is overselling.
So how much can anyone really see in there?
Enough to name features, not enough to read the whole mind. It's the interpretability work, reading a model like a brain scan. Check the exact term, but the principle holds. We grew it, and we're still learning to read what grew. But you two see the everyday side of this more than I do. Give them the punchline.
Watch it, start to finish. You begin with a wall of random dials, pure noise. You show it an example, it guesses, you score how wrong it was, you walk the blame backward through the layers, and you nudge every dial a hair downhill. One tiny boring step. Then you do that 1 trillion times over a mountain of examples, and slowly, with no one writing a single rule, the dials arrange themselves into something that reads faces, writes sentences, answers your questions. The intelligence isn't programmed in. It precipitates out, like crystals forming in water. And that, start to finish, is how neural networks learn.
Perfectly said. Mirzal, the last word is yours before we let you go.
Only this. We built the learning, not the answers, and I love that it lands stranger than any magic trick would. Thanks for having me on.
And that's the line nobody says out loud. They didn't write the answer. They wrote the learning and let the answer fall out. Once you see that, you can't unsee it.
That boundary she drew is the honest part, and it changes how I hear the whole word learn.
I'll give it the concession. It's real learning, genuinely. It's also, in the end, a very confident guessing machine that got very good at guessing.
Both, Fenrir. Which is exactly what makes it worth understanding instead of fearing.
So if you keep nothing else, keep this. A neural network is a wall of random dials that practices its way out of the noise. It doesn't get told the answers. It gets told how wrong it is, and it walks downhill from there.
Not a computer at all, really. And the payoff for you is this. The next time someone tells you an AI mysteriously learned something, you'll know there's no mystery in the machinery. Somebody set up a wall of dials and let 1 trillion tiny corrections do the rest. You can explain that at dinner now.
And next time, we open the file. If a model is just a giant list of these two numbers, what does that file actually look like? And could you really print one out? That one surprised even me.
For the record, I still land where I landed. It's real learning, and it's a spectacularly good guessing machine. Both. I'm keeping the word guessing.
If any piece of this finally made the machine make sense, do us one favor and subscribe. This series builds the whole picture one layer at a time, and I'd like you in the room for it. And here's the one we couldn't settle today, so take it to the comment. If nobody can fully explain what a network learned, is it still just math, or has it become something new? That's the one to argue about. For Erica, Tiffany, and Fenrir, I'm River. Thanks for staying to the bottom of the hill with us, and we'll see you in the next one. Less noise, more signal. Until next time.
River, that was a keeper. 8.7 and a request for a follow-up episode. This is Professor Erica. Thanks for watching and signing off.